All right, so welcome back, Julian. This is the second chapter of Chem 111, and that is laws of chemical combination, quantum numbers, and electronic structure of atoms. So it's approximately three topics combined in one. All right, so very briefly, we start with the first part, which is the laws of chemical combination. And there are basically four laws of chemical combination, basically four. The first is the law of conservation of mass. The second is the law of definite proportion, also called the law of constant proportion. The third is the law of multiple proportion. And then the fourth is the law of reciprocal proportion. Okay? So, and we take the first one, the law of conservation of mass. Now, the law of conservation of mass is championed by Landau and his co-workers, okay? So Landau and his co-workers actually championed this law. This law was actually propounded by them based on John Dalton's theory, which states that matter can neither be created nor be destroyed, but can be transformed or converted from one form to another. That is the basics of this law of conservation of mass. So according to Landau and his co-workers, the law of conservation of mass states that in a chemical reaction, mass can neither be created nor be destroyed. That is to say that the sum of the total mass of the reactant of a chemical reaction must be equal to the total sum of the product of that same reaction. No mass is lost in the process. That is what the law is saying. Now, the law is verified using Landau's experiment. The Landau's experiment comprises of a Landau tube that is H in structure. In that tube, one side of the tube, you can have sodium chloride solution. The other side of the tube, you have silver triazonitrate 5 solution. Of course, you take the weight before the reaction because the tube is privileged to separate the two chemicals from meeting with each other. So the weight is taken, probably it weighs 100 grams, and then the tube is now inverted and shaken vigorously and allow the reaction to take place between the two substances. And of course, when sodium chloride reacts with silver triazonitrate 5, a precipitate will be formed. A precipitate of what? Of silver chloride will be formed. A white precipitate for that matter. So that white precipitate formation shows a complete reaction, okay? So the white precipitate being formed will determine the completeness of the reaction, and then the weight will be taken for the second time. And if it gives you exactly 100 grams, that shows that the law actually is true. And of course, it is true from that experiment. So, but however, limitations in this law states that one, it is only applicable in liquid substances or aqueous substances. You do not apply this law in solid or gases. Solid because solids react very slowly. You do not apply it in gases because the mass of gases are very much unpredictable, okay? So that is the very first limitation you can have as far as the law of conservation of mass is concerned. Then the second limitation is that the volume of the Landau tube expands, especially for reactions that are exothermic. You know, it expands and doesn't return back to its original shape. Then the last limitation you can have is that in the presence of sunlight, especially nuclear reactions, in the presence of sunlight, Landau's law doesn't hold. And the reason is because sunlight actually converts mass into energy. If you remember Albert Einstein's equation, mc squared, mass times light will give you energy. So it converts part of the mass into energy, which can be used, doped, and at the end of the day, the mass of the reactant becomes greater than the mass of the product. And so the law does not follow. So these are the limitations of the law of conservation of mass. Now that takes us to the second part, which is the law of definite proportion. Now, according to the law of definite proportion, also called the law of constant proportion, of course, first and foremost, it is championed by Prout in 1799. Prout in 1799 actually, discovered this law based on John Dalton's theory, which states that atoms of the same element are identical, but completely different from atoms of other elements. Oh yes. Atoms of the same element are identical, but they are completely different from atoms of other elements. So after a series of experiments performed by Prout, he stated that all pure samples of the same compound contains the same element chemically combined together in the same proportion by mass. All pure samples of the same element or of the same compound contains the same element chemically combined in the same proportion by mass. Take water for example. All pure samples of water contains the same elements chemically combined in the same proportion by mass. It comprises the same 2 atoms of hydrogen and 1 atom of oxygen chemically combined by mass. If the water is coming from the lake, if it is coming from the ocean, if it's coming from the well, it's coming from the sea, it's coming from rain, no matter where the water is coming from, when it is purified, it contains the same proportion by mass of hydrogen and oxygen, and that proportion is 1:8. 1:8, 1 from hydrogen, 8 from oxygen. You know, hydrogen is 1. The mass of hydrogen is 1. 1 times 2 is 2. The mass of oxygen is 16. So by the time you find the ratio, it gives you 1:8. That is the law of definite proportion, the law of constant proportion, right? So that takes us to the third law, which is the law of multiple proportion, championed by John Dalton himself. Yes, championed by John Dalton himself, based on his fourth theory, which states that chemical combination, or let me say chemical atoms chemically combine together with each other in simple whole number ratios. That is the bedrock of this law of multiple proportion, championed by John Dalton himself. His statement that says that atoms chemically combine together with each other in simple whole number ratios prompted this particular law of multiple proportion. And this law states that elements, if 2 elements A and B combine chemically with each other to form more than 1 compound, then the several masses of A, which combines with a fixed mass of B, are in simple whole number ratio. All right, let me give you an example on that. Let's say A be oxygen and B be copper, okay? Copper 1 to be precise. If oxygen and copper 1, that's a fixed mass of copper, combines chemically to form more than 1 compound, that is copper 1 oxide and copper 2 oxide, then the several masses of oxygen, which combine separately with a fixed mass of copper, are in simple whole number ratio. Do you get? So let's take a fixed mass of copper combining with oxygen. Now, the first copper combines with oxygen to give you copper 1 oxide. Then the second one combines with oxygen to give you copper 2 oxide. Now, the fixed masses of copper kept aside, those masses of oxygen which combine separately with copper are in simple whole number ratio. And the first oxygen there is half a mole. The second oxygen is 1 mole. By the time you do your ratio combination, you discover that it is in the ratio 2:1. And that is the law of multiple proportion by John Dalton. So that takes us to the third one there, which is the law of reciprocal proportion. And the law of reciprocal proportion actually is coined by Benjamin Richter Jeremias in 1792. Benjamin Richter Jeremias in 1792. And this law states that when elements A combines with 2 or more other elements, say B and C, then the several masses of B and C, which combines with a fixed mass of A, are in same or multiple of B and C, which combines with each other without A. I know this is a little bit confusing, but let me take it again. This law states that when an element A combines with 2 or more other elements, let's say B and C, then the several masses of B and C, which combines with a fixed mass of A, is the same or multiple ratio of B and C combining together without A. To give you a typical example, a combination between carbon, hydrogen, and oxygen. Take, for example, carbon combines with hydrogen to give you methane. The same carbon will combine with oxygen to give you carbon 4 oxide. Now, hydrogen can actually combine directly with oxygen to give you water, right? Now, what the law is saying is that when an element A combines with 2 or more other elements B and C, that means when carbon combines with 2 or more other elements, hydrogen and oxygen, when carbon combines with hydrogen and oxygen, then the several masses of B and C, which combines with a fixed mass of A, then the several masses of hydrogen, and oxygen, which combines with a fixed mass of carbon,
are the same or multiple ratio of hydrogen and carbon combining together without A. That simply means that the masses of hydrogen that combines with carbon, the masses of oxygen that combines with carbon are in the same ratio or multiple ratio as at when hydrogen will combine with oxygen without including carbon. That is what the law is saying. And the best way to do that is always to put them in the ratio of their masses. Carbon combining with hydrogen will do that in the ratio of 12:4. 12 is to carbon, 4 is to hydrogen. While carbon combining with oxygen, we do that in the ratio 12:38. And when hydrogen combines with oxygen, we do that in the ratio of 4:16. So 12 grams of carbon combines with 4 grams of hydrogen. Then 1 gram of carbon, that's a fixed gram of carbon now, will combine with how many? And by the time you're able to do that mathematics, you store that mass of hydrogen. So you do the same for oxygen, store that mass of oxygen, and then find their ratio. You will discover that the ratio you're going to have for those fixed masses that combine with a fixed mass of carbon is going to be in the ratio of 1:8. Now check hydrogen combining with oxygen directly will do that in the ratio of 1:8 as well. So that is the law of Landau. I say Landau. That is the law of Benjamin Richard Jeremias. Other examples which you can use to work out this law of reciprocal proportion is oxygen combining with sulfur and hydrogen, and then phosphorus combining with hydrogen and chlorine, then the fixed mass of hydrogen combining with sodium and chlorine, So the ones at the top are always fixed masses, right? So you can make those experimental research and you get rid of that. So that takes us to the second part, which is I think this chapter is divided into 3. We go to the quantum number realm, but before we enter quantum number realm, we look at Niels Bohr's theory of the hydrogen atom. Very, very important. Niels Bohr's theory of the hydrogen atom. Now, according to Niels Bohr, when electricity is passed through a discharge tube containing hydrogen gas at low temperature, the molecules of hydrogen gas breaks down into hydrogen atoms, which eventually emits radiations. These radiations emitted are electrons. So once you pass electricity through a tube containing hydrogen gas, it breaks down the hydrogen gas and they emit their electrons. These electrons fall in the form of lines, and these lines can be viewed by the use of a spectroscopy or a spectroscope, as the case may be. Now, these lines are grouped under series and regions, okay? So you have series like the Lyman series, the Balmer series, the Paschen, the Brackett, the P-Fon. Sorry, there's nothing like P-Fon. It's the Fon series, okay? The Fon series, Humphrey, and further series. Then as for the region, you talk about the UV region, the visible region, the infrared region, and then the far infrared region, as the case may be. So now, let's look at the spectrum of line of the hydrogen atom. The very first ground state is a nucleus. After the nucleus, you have the first energy level, the second energy level, the third energy level, fourth, fifth, sixth, on the above 6th energy level. Now, the electrons that will be falling from the second energy level to the first energy level is the first spectral line of the hydrogen atom. The ones falling from the second to the first. Then the others will fall from the third to the first. Others will fall from the fourth to the first, the fifth to the first. All those falling on the first line are referred to as the Lyman series. Okay? So they are grouped under the Lyman series. Then those coming from the third to the second, from the fourth to the second, from the fifth to the second, from infinity to the second are grouped under the Palmer series, okay? While those falling from the fourth to the third, from the fifth to the third, from the sixth to the third, seventh to the third, infinity to the third are grouped under the Brackett series. Those falling from the sixth to the fifth, like that, are grouped under what we call the Brackett series. You have the Fon series, you have the Humphrey series, and all that. So that is just how it works. Now, the first line of the Brackett series, we have N1 and N2. N1 simply signifies the series, while N2 stands for the level where the electron is falling from, okay? So the first line of the Balmer series actually has N1 as 2 because it is the Balmer series. Then the first line is falling from the third level to the second level. So automatically your N2 is 3. So you can actually find the second line of the Balmer series, third line of the Patchen series. You can give those multiple exam questions for your students to play with. And then that takes us to the wavelength. These electrons fall with a given wavelength. They fall with a given velocity. So the velocity with which these electrons will crash at each of these levels is given by the reciprocal of lambda, which is the wavelength, which is equal to Rydberg's constant, open a large bracket, 1 all over the square of n1 minus 1 all over the square of n2. N1 signifies the series where all of them are falling to, while N2 signifies the level where they are coming from, okay? So you can always make your hypothesis right. Then the Rydberg's constant is 1.097 times 10 raised to the power 5 per centimeter. You can always convert that to meters. And remember, examiners at times will want you to put your answers in nanometers, okay? So you can always do that. Nanometer is 10 raised to the power minus 9. Remember, milli is 10 raised to the power minus 3, micro 10 raised to the power minus 6, nano 10 raised to the power minus 9, pico 10 raised to the power minus 12, femto 10 raised to the power minus 15, octo 10 raised to the power minus 18, zemto 10 raised to the power minus 21, yocto 10 raised to the power minus 24. The last three are the ones that always escapes your memory, and that is the octo, zemto, and yocto. Just remember Azi. You know, Azi, Anele Dumzo Ajofo, Kano, Okoro, and Obo families. Azi. So A there for octo, Z there for zemto, the Y in the Z is the yocto, right? So you can always remember that very well. So as far as the regions are concerned, the only UV region is the Lyman series. The only visible region is the Palmer series. As for the Paschen, the bracket, and the Fon series, they are the infrared region. As for the Humphrey, is the far infrared region. Then it is also important for you to know the energy in terms of electron volt at each of these energy level, right? The first energy level is minus 13.6 electron volt. The second energy level is minus 13.6 all over 2 square electron volt. The third energy level is minus 13.6 all over 3 square electron volt. So the formula actually is minus 13.6 all over n square electron volt, right? Now, this tells you the energy at each energy level, okay? Very, very important. And then it's important for you to know that this energy is equivalent to minus, that is to say minus 13.6, sorry? All right, let me put it this way. The energy possessed by an electron at the ground state is equivalent to minus 13.6 electron volt, which is equal to minus 2.8 times 10 raised to the power minus 18 joules, okay? It's also important for you to know that 1 electron volt is 1.602 times 10 raised to the power minus 13 joules of energy, right? So at times you can be asked to calculate the difference in energy from the first and second energy level. And to do that is simply minus 13.6 open bracket 1 all over the square of n2 minus 1 all over the square of n1, you know, stuff like that. So some hypothetical questions that can come under this series lines are, they may just one of a sudden ask you, how many spectral lines are there when an electron drops from the 5th orbital to the 1st orbital of the hydrogen atom? How many spectral lines? If you count that properly, you're going to get 4 spectral lines. Next can be, what is the wavelength of the first line of the Balmer series? So all you need is just the first line. Look for your N1 and your N2 and you'll be good to go. Now, what is the wavelength of the first and the fourth line? You should be able to hypothesize that without problem, right? So next, that takes us to Nelbo's theory of an electron. Now, J.J. Thomson actually in his definition says that an atom comprises of a proton and electron scattered inside a sphere in the form of pumphoody, you know. Rutherford, however, said that no, that rather an atom is made up of a central nucleus surrounded by clouds of electrons, you know. Now, Nelbo actually looked at these two guys' definition and came up with the following postulations. Number one, he said electrons do not radiate energy so long as they remain in an orbit. Because according to J.J. Thomson, electrons cannot be revolving around the nucleus that is made up of positively charged proton, that they are all scattered inside. So Niels Bohr said, electrons do not radiate energy so long as they remain in their orbits. So that kicked that up. Then the second postulation is that electrons will only radiate energy when they jump upwards, or let me just say towards the nucleus. For them to jump towards the nucleus, they will definitely radiate energy, or they will absorb energy when they jump away from the nucleus. You know, for you to jump away from the nucleus as an electron, if you are jumping towards the nucleus, you need little energy, because there is a positive charge in the center of the nucleus that will attract you. So you actually radiate energy at that point. So for you to jump away from the nucleus, you have to absorb external energy, external power to overcome the force of attraction coming from the nucleus. Okay, so that is Niels Bohr. And then lastly, he said that the electrostatic force of attraction between the electrons and the nucleus must be equal to the centrifugal force on the orbitals. And that simply means that there will be no time when electrons revolving around the nucleus will radiate their energy and be sunk into the nucleus. It will never happen. So according to Niels Bohr, the atomic model can be designed in such a way that electrons revolve in fixed path around the nucleus. So he was more or less like dancing to the tune of Rutherford, because the fact there is that Rutherford was more correct than J.J. Thomson. Okay, so according to Niels Bohr, he said there are fixed paths in which electrons revolve around the nucleus. He called this path shells or energy levels, and he named them K, L, M, N, O, P, Q as the case may be. And for each of them, he named their energy level starting from the first shell as the 1, second shell 2, 3, 4, 5, 6 as the case may be. And that led to the birth of the quantum number theory. And of course, the birth of the quantum number actually is an amazing experience in chemistry, because the concept of the quantum number helps us to determine the behavior and the arrangement of electrons within the main and even the subshell of an atom. That is the whole concept of the quantum number, just to determine the behavior and the arrangement of electrons within the main and the subshell of an atom. That is it. As simple as that. So there are basically 4 quantum numbers that will guide the behavior, the arrangement of electrons within shells. 4 quantum numbers. The first is the principal quantum number, represented by n. The second is the angular momentum, or simply called the azimuthal or subsidiary quantum number, represented by L. The third is a magnetic quantum number, represented by ML. And then finally, the spin quantum number, represented by MS. As for the principal quantum number, it simply helps us identify the size of the atom based on the shell type. Okay, so for example, the K shell is the first shell, and the total number of electrons that can be accommodated in a particular shell is given by 2n squared. So for the K shell, where n is equal to 1, it has a maximum of 2 electrons. For the L shell, it has a maximum of 8 electrons. For the M shell, a maximum of 18 electrons, like that. So that takes us to the next, which is the angular momentum, or the azimuthal or subsidiary quantum number. Now, the angular momentum describes the type and the shape of the orbital occupied by an electron. The type, the shape of the orbital. Which type? Is it SPDF? What shape? Is it dumbbell? Is it double dumbbell? Is it spherical? Is it complex? So the angular momentum will help us describe the type and the shape of the orbital occupied by the electrons. And of course, it takes its value from 0, 1, 2, 3, 4. The n is n minus 1. When L is equal to 0, then the orbital is the s orbital. When L is equal to 1, it is a p orbital. When L is equal to 2, is a d orbital. When L is equal to 3, is the f orbital. And of course, their shape for spherical is, for s orbital is spherical. For the p orbital is dumbbell. For the d orbital is double dumbbell. For the f orbital is complex. Take note, the SPDF actually came from the word sharp for S, principal for P, diffuse for D, and fundamental for F. So simply say sharp, principal, diffuse, fundamental, SPDF. Now that takes us to the magnetic quantum number. The magnetic quantum number actually is simple enough to tell us the number of orbitals present in the subshell of an atom. How many orbitals are present in the S? 1 orbital. How many orbitals are present in the P? 3 orbitals. How many orbitals are present in the D? 7 orbitals. Sorry, 5 orbitals. How many orbitals are present in the F orbital? 7 suborbitals. Now the gospel truth is, how do you get these numbers? Apart from telling us the number of orbitals present in a subshell, apart from telling us the number of subshells present in an orbital, it also describes the orientation of the electrons in the X, Y, and Z plane of the Cartesian plane. So it also describes orientation. Take note. Now, how does it tell us the number of subshells present in an orbital? It does that through the formula 2L plus 1. So ML is simply 2L plus 1. When L is equal to 0, what happens? That means that your ML is equal to 1. And of course, that means your ML is equal to 1. And that is simply the S orbital, okay? So when L is equal to 1, that means 2 times 1 plus 1, that's going to give you how many? That's going to give you 3. And for you to have 3 there, it simply means that you're going to have 3 values. It ranges from positive to negative, okay? So the first subshell is going to be plus 1, the middle subshell is going to be 0, the last subshell is going to be minus 1. So you continue like that. If L is equal to 2, 2 times 2 plus 1, that's 5. So you're going to have 5 subshells, and each of these subshells are labeled from minus to positive. So you start with minus 2, minus 1, 0, like that, and you'll be able to get those values. Those values will tell you the numbers, okay? So that takes us to the last one, which is the spin quantum number. And the spin quantum number actually will simply tell us the direction of spin of the electrons. If the electrons are spinning in the clockwise direction, they have a positive spin of 1/2. If they are spinning on the opposite direction, which is the anti-clockwise direction, they have a negative spin of minus 1/2, as the case may be. All right, so basically those are the information you should remember, and remember vividly. So now you can just be overall as the K shell, just to to break down what you have studied into bits. The N shell, for example, where the energy level is equal to 4. So for N to be equal to 4, that means that your values of L is going to be 0, 1, 2, and 3. So it's best recognized by simply saying the N equals 4, subtract 1 from it, you get 3. So you start with 0, 1, 2, 3. Now 0 there signifies the S orbital, 1 there signifies the P orbital, 2 there signifies the 3 there is the D orbital, where 3 signifies the F orbital. We've done that before. Now because N is equal to 4, you are going to assign 4 to all of these orbitals. So it's going to be 4S, 4P, 4D, and 4F. So this is called degenerate orbitals. An exam question may just come. What is the number of orbitals in an N shell? An N shell has a total of 1, 3, 5, 7, which is 15 orbitals. How? Because in an N shell, the energy level is 4. The value of L is 0, 1, 2, 3, which is S, P, D, F. And then the S has 1 orbital, the P has 3 suborbitals, the D has 5 suborbitals, the F has 7 suborbitals. So by the time you add all these suborbitals, it will give you a total of 15. And that simply means that it has 15 orbitals. Because they have the same energy level, which is 4s, 4p, 4d, 4f, you refer to them as degenerate orbitals. So another exam question can come: how many degenerate orbitals are there in the M shell? And the gospel truth about M shell is that N is equal to 3, L will be 0, 1, 2, which is equivalent to SPD. And then, of course, because it's 3, it's going to be 3s, 3p, 3d. So they have the same energy level, and therefore they are degenerate orbitals. So how many orbitals are there? The S is made up of 1 orbital, the P is made up of 3 orbitals, the D is made up of 5 orbitals. So that gives you a total of 9 orbitals in what? In the M shell. So at times, if they ask you, how many degenerate orbitals are there in aluminium? You will first of all determine which shell aluminium falls into. Okay, once you determine the shell it falls into, you know your value of n, get your value of L, get the degenerate orbitals, get the number of subshells, add them together, and you're good to go, right? So now, typical exam questions will come. Represent a particular number, a particular element in the 4 quantum numbers. Very, very important. Represent them in the 4 quantum numbers. For example, they will ask you, what is find the quantum numbers of the valence electron in fluorine. Find the quantum number of the valence electron in fluorine. How will you be able to do that? Find the quantum number in the valence electron of fluorine. First, write the configuration of fluorine: 1s2, 2s2, 2p5. Now, the valence electron of fluorine is on the p orbital. The p orbital is made up of 3 subshells, right? So, because there are 5 electrons, that means there's only going to be one shell that is without electron. Good. And those 3 orbitals are -1, 0, and 1. So the valence electron is on the last orbital. And that simply means that the value of n, first and foremost, is 2. Why is it 2? Because it is on the second energy level. The value of L is going to be 1. Why is it going to be 1? Because the p orbital there is 1. Because that is on the p orbital that the last electron is. Then the value of ml will now be on the shell the last electron falls into. If the last electron is falling into the last shell on the right, which is 1, that means the value of ml is going to be 1. If it is falling on the middle, the value of ml is going to be 0. If it is falling on the first, the value of ml is going to be -1, depending on the orbital. Then the last one is the spin. The spin now is the direction of the last shell, of the last electron. Is it facing upward or facing downward? As far as this one is concerned, it is facing downward, so it's going to be a negative spin. If it was facing upward, it becomes a positive spin. Okay, all right, so basically that is that for that. So that's takes us into the configuration RAM. So we are going to look at electronic configuration. This is one of the longest chapters, bro. Come on, this chapter is pretty long. This is over 30 minutes we have been discussing, yet we are not done with this chapter. So that takes us to electronic configuration. Good. So you already know how to, arrange configuration. Start with n equals 1, that is 1s, n equals 2, 2s, 2p, n equals 3, 3s, 3p, 3d, and then you use the arrows to, pick them and order. But there is a shortcut to remember this very, very well. There is a shortcut to remember it. And the shortcut is simple. First of all, write your S, P, D, F. Label them 1, 2, 3, 4 at the bottom, okay? So the first thing to do for you to get this arrangement without stress is, first and foremost, write your S, double it. So it's going to be 2s, s, and s again. Now, the second orbitals that we follow, you start from P and move backward to S. It was S, P, D, F. The first S, you write it 2 times. Now, when you go to P, you move backwards. So it's going to be PS. So you now have PS. You do it 2 times. PS again. When you're done with that, you go to D orbital. From the D orbital, you move backward. You're going to make DSP. So you write that 2 times as well. DSP. When you're done with that, you go to the F orbital. F, going backward, you're going to have FDSP. Do that 2 times. FDSP. When you're done doing that, those numbers that you wrote at the bottom are the numbers you are going to start in numbering each of the orbitals. What do I mean? Under S, you have 1. So you start with 1. The second S orbital, you put 2, which is the energy level. The third S orbital will be after P. After P, as the case may be, you put 3. The next one will be after 3p, you put 4, 5. So number all the S, starting from 1 till wherever you stop. Then for the second orbital, which is the P, you start with 2. So from 2, go to 3, 4p, 5p, 6p, 7p, like that. And the same thing applies to D. For D, you start with 3, 3D, 4D, 5p, 5D, 6D, and all that. F starts with 4F, 5F, like that. So that gives you the order. Of course, you already know the maximum number of electrons each of them can carry, and that makes your work easier and fast. Pauli exclusion principle. According to the Pauli exclusion principle, the law simply states that no 2 electrons in an atom can have all 4 quantum numbers equal. It is not possible, and it is never done. N can either be 1, L can either be 0, ML can be 0, MS will be plus half. You cannot have N as 1, L as 1, ML as 1, MS as 1. It's not possible. Or better still, you cannot have two electrons having the same 4 quantum numbers, in the sense that you cannot have N1, L0, ML0, MS plus half. The second electron will now be also ML1, L0, ML0, and then MS plus half. No. So the variation is going to come in the spin of the electrons, which is positive or negative. Okay, so that is only where the variation in their differences will come into play. So according to Pauli exclusion principle, it is not possible to have all 4 quantum numbers of electrons in the same atom to be equal. It's not possible, and it is never done. Next is the Hund's rule of maximum multiplicity. Of course, the Hund's rule of multiplicity simply says that you have to first of all share electrons 1-1 before you pair, okay? So you have to share 1-1 before pairing occurs. Finish a particular energy level before going to another energy level is Hofburg's principle. Hund's rule of multiplicity means share 1-1 before pairing. Now, according to Hofburg, you have to finish one energy level before you enter another one. Another way you can define Hofburg's principle is by saying that degenerate orbitals must be filled completely before filling higher energy levels. That's still the same language, just that degenerate came into play. Okay, so that takes us to the last one there, which says that each orbital must contain a maximum of 2 electrons with opposite spin. You can't have a suborbital having 3 electrons inside. That's madness. Come on. It's 2 maximum with opposite spin. That is what that part is saying. Now, a typical exam question may come and ask you for electrons or elements actually that do disobey Hund's rule of multiplicity and even Hofburg's principle. We have elements that actually disobey these guys. And the gospel truth about it is that we have about 14 of them in the entire periodic table. The most common one that the university will always draw your attention to are chromium and copper. Okay, chromium is known to have an atomic number of 24. Chromium will rather make sure that its d orbital are completely partially filled by stealing 1 electron from the s orbital. Copper will steal 1 from the s orbital to completely fill its d orbital to make it 10. Copper 1 will have 10 in its d orbital and 0 in its s orbital. Copper 2 will have 9 in its d orbital and 0 in its s orbital. Very, very important. And that makes copper 1 diamagnetic, while copper 2 paramagnetic. We're going to come to all those paramagnetism and diamagnetism brouhaha so that you get the message clear. So we say there are a total of 14 of them. Let's start with the argon series. We have the argon series, we have the krypton series, we have the xenon series. The argon series actually has about 4 elements in the argon series that disobeys these rules. And these 4 elements are chromium. Did I say 4? It's not actually 4. There are actually 2 elements in the argon series, chromium and copper, right? Now for the krypton series, you have 5 that disobeys the rule. And the 5 that disobeys the rule are, the 5 that disobeys the rule in the krypton series are lanthanum. Lanthanum is the first, followed by molybdenum, followed by palladium, and then you have the last one there, which is rhodium. Okay, lanthanum, molybdenum, palladium, and rhodium. They are in the krypton series that disobeys the Hofburg principles and that of Hund's rule of multiplicity. Then the xenon series have about 5 of them, and sorry, I think I made a mistake. It's not actually 14. There are a total of 12. Okay, 12 elements that disobey Hund's rule of multiplicity. 12. 2 from the argon series, and then you have 5 from the krypton series and 5 from the xenon series. I have given you the 5 in the krypton series. Now let's look at the 5 in the xenon series. The 5 in the xenon series, the first one you have there is lanthanum. Lanthanum is in the xenon series. Sorry, rhodium. Ruthenium is for the krypton series. I think I should take them back again so that you have a better understanding. I think I made some mistakes somewhere. All right, let me take it again. First, let's start with the argon series. There are two of them, which are the popular chromium and copper, okay? Chromium and copper. Those are the two disobedient guys in the argon series. Now we go to the krypton series, which are 5 in number, which are number 1, the ruthenium. Ruthenium is the first, followed by molybdenum, palladium, and rhodium. So they are 5 in number. Ruthenium, molybdenum, palladium, rhodium, right? And then rhodium, I think that's rhodium. And then silver, that makes it 5. Silver, that makes it 5. All right, so once again, ruthenium, palladium, molybdenum, silver, and rhodium. Those are the 5 disobedient guys in the krypton series. Krypton 36, of course. Then the xenon series, which is the xenon 54, they are 5 in numbers. And the first one there is the lanthanum, followed by the cerium, followed by the gadolinium, and then you also have the gold, and then finally you have platinum. So you have platinum, you have gold, you have gadolinium, you have cerium, and then you have the almighty lanthanum. Now take note, cerium happens to have a peculiar configuration because it is more or less like a dividing block between the lanthanum series and it's peculiar because it's a division. It stands in between the F block and the D block series, okay? So if you look at the configuration of cerium, it's going to have 1 electron on the F orbital and 1 electron on the D orbital. Yeah, 1 electron on the F and 1 electron on the D orbital. The argon series is argon in bracket 4s 3d. The krypton 36 series is 5s 4d. So it's almost the same thing with argon series. The only difference is the energy levels have increased by a factor of 1. 4s 3d. As for krypton, instead of 4 it becomes 5s. Instead of 3d it becomes 4d. You get it? Good. So next is the xenon series. The xenon series is 6x, 4f, and 5d. You have to remember that. All right, so now that we have been able to look at the all disobedient guys, that takes us to the very last part of this chapter, which is simply lanthanides. I say lanthanides, which is simply paramagnetism and diamagnetism. So what is paramagnetism? Paramagnetism means partially filled orbitals or partially filled electrons in the outermost shell or outermost orbital of an element. You know, it has unpaired electrons. The presence of unpaired electrons makes a particular compound or element or molecule to be paramagnetic. Diamagnetic elements are those elements that have completely filled electrons in their orbitals. They have no unpaired electrons and they are in their last shells or their last orbitals, as the case may be. Now take note, the number of unpaired electrons is responsible for the magnetic attraction experienced by elements or molecules in a magnetic field. The reason is that these unpaired electrons form a negative charge, which in turn creates a pole of attraction in a magnetic field. And of course, the level of attraction is dependent on the number of unpaired electrons. Those that experience attraction are paramagnetic, while those that do not experience attraction are diamagnetic. For example, oxygen is paramagnetic in nature. Why? That's oxygen molecule is paramagnetic, while nitrogen is diamagnetic. We're talking about nitrogen molecule. Now, you can actually determine the paramagnetism and diamagnetism of a substance based on whether they are atoms or molecules. As for the atomic part, is the simplest one to do. Just write a configuration and check if there are unpaired electrons in the last orbital. If there are, conclude that it is paramagnetic. If there are no unpaired electrons, like neon, conclude that it is diamagnetic. Right? Good. This is for atoms. Now for molecules, there is a little more exercise to do. And the little exercise is based on the atomicity of the molecule. Oxygen, for example, has an atomicity of 2. So you write a structured electronic configuration of oxygen. Tell us the number of unpaired electrons it has. If it has 2 or 3 unpaired electrons, all you need to do is just to multiply the number. Sorry, did I say the number of unpaired electrons? No. So what you are supposed to do is to simply sum up the number of electrons in the last orbital. That's the p. For example, if it is on a p shell, maybe it's p5. Sum up the 5. After summing them up, multiply it by the atomicity, and then use the standard to start, assigning electrons following Hund's rule from the bottom to the top. If you end up having one unpaired electron in any of the orbitals, declare it paramagnetic. If the last electron is like completely filling a particular box, declare it diamagnetic. So basically, that is how to recognize paramagnetism and diamagnetism as far as those elements are concerned. Then it's important for you to know that ferromagnetism is a type of magnetism whereby all the electrons are actually facing vertically upward. And a typical example of ferromagnetism is iron. And ferromagnetism happens to be a type of paramagnetism, because if you are not paramagnetic, you're diamagnetic. So ferro is a subset of paramagnetism, and the only example we have right now under the umbrella of ferromagnetism is iron and other transition elements, e.g. cobalt, nickel are ferromagnetic. So there are 3 elements in the periodic table for now that are ferromagnetic. Number 1, iron. Number 2, cobalt. And number 3, nickel. Now, as for antiferromagnetism, a typical example of it is chromium. And you have to remember that keyly. Chromium, antiferric magnetism. So, ladies and gentlemen, that is the end of this chapter. It was quite long and time consuming. However, we've gotten to the end. See you in the next chapter. And the next chapter is the almighty hybridization. Boom.